Hi, we're going to talk about igneous rocks today. Igneous rocks, of course, are rocks that formed from the cooling and solidification of lava or magma. If we didn't memorize this, we can find it in the rock cycle of Earth's crust diagram in the reference tables on page 6. You can see igneous rocks. You want to look at the arrow pointing towards igneous rock, solidification, changing from a liquid to a solid. And before that, it's rock in its liquid form. We call it magma, underground lava on the surface. So any rock, all three rocks can melt to form magma and then solidify to become igneous rock. It can happen in lots of different ways. Some differences include where it cools, above ground or below, how long it takes to cool, its location on Earth, whether it's in the continent or an ocean, and the type of minerals inside the rock. So this picture shows two different types of igneous rocks, extrusive and intrusive. Igneous rocks can form deep inside the Earth or at the Earth's surface. It causes a big difference in how long it takes the rock to cool. So because they're insulated and surrounded by other rocks, the intrusive igneous rocks, the magma underground, cools very slowly, and the extrusive igneous rocks on the surface cool very quickly. So we'll start with intrusive. Beneath the surface, magma takes much longer to cool. When we're talking on a scale of millions of years, it gradually solidifies into an intrusive igneous rock. That long cooling time allows for large mineral crystals to grow. So large for a mineral crystal is about the size of a grain of rice, 1 to 10 millimeters. We call that texture coarse. Here's a rock sample with coarse texture. An extrusive igneous rock, on the other hand, cools at the surface. Temperatures are much lower, so the lava will cool quickly. We call them extrusive igneous rocks. Because there's only a little bit of time for them to cool, only tiny mineral crystals form, or none at all. We call that texture fine, like this rock right here, or this rock. Or we call it glassy, like this rock right here. Fast cooling leads to only the formation of small crystals, no crystals, or sometimes gas bubbles, is in the case with this rock right here. The lava is cooling, gases are being released, the lava cools while the gas bubbles are still trapped inside the magma or inside the lava, and so it hardens into a rock around those gas bubbles. So that's an indication of fast cooling. So cooling time tells us the texture. So these three rocks, which are small crystals, no crystals, or gas bubbles, cooled quickly. We call them fine, glassy, or vesicular texture. Vesicular means gas bubbles. These rocks with bigger crystals indicates the slower cooling, coarse or very coarse texture. So rocks can also form in different locations on the Earth. They could form in the continents or they could form in the oceans. Because the minerals that make up the rocks on the continent are different from those in the oceans, you end up with a different type of rock. So minerals that make up the rocks on continents are light in color. We called them felsic because they contain feldspar and silica. At the bottom of oceans, the minerals are denser and darker in color. We call them mafic because they're rich in magnesium and iron. Iron's symbol on the periodic table is Fe. So we have lighter colored minerals, darker colored minerals, and then a whole range in between. So you can see the rock on the left is much lighter color, so we would call it felsic. The rock on the right is much darker in color, so we call it mafic. So the color, lighter colored minerals like these, lighter colored rocks like these, darker colored rocks like these. The color tells us the mineral composition, and from that we can infer whether it formed on a continent or in the ocean. So lighter colored minerals indicate that they formed on continents. Darker colored minerals, mafic minerals, formed under the oceans. So again, to summarize, texture or crystal size tells us the cooling time. Like, is it intrusive, meaning it cooled underground, or is it extrusive, it cooled on the surface? Also, we can infer if it cooled slowly or quickly. So what we see is the texture or the crystal size. What we can infer is the cooling time. What we see is the color, and what we can infer is the composition. So is it felsic composition or mafic, right? Dark colored, light colored. And did it form in the continent or the ocean? So lighter colored minerals formed in continents from continent crust, and the darker colored minerals formed in ocean crust. So we end up with a grid that looks something like this. Fine texture or small crystals toward the top, coarse texture or large crystals towards the bottom, and color left to right. Light colored felsic on the left, dark colored mafic on the right. And if we had a rock in this location, it would be a fine texture rock with dark colored minerals. So page 6 of the reference tables gives us this exact diagram and the ability to interpret, identify the rocks based on those physical characteristics. So on this left-hand side, we're going to block out the bottom for now. On the left-hand side, we see environment of formation. You can see intrusive and extrusive under that. Directly across, where it's circled in green, you can see the crystal size and the texture. So at the top, we have no crystals and glassy, and then the crystals get larger as you go to the bottom of the chart. Fine, coarse, very coarse texture, indicating that longer cooling time. You can also see vesicular hiding over next to glassy and fine on the edge. In the middle, we have the names of the rocks. Directly underneath that, we have color, density, and composition. The range from the left-hand side, lighter color, lower density, felsic composition, over to the right-hand side, darker color, higher density, mafic composition. And at the very bottom, we have the minerals that you would find in these rocks, right? The mineral composition. We'll go over that in a few minutes. We're going over that right now. So how do you know which minerals are in the rocks? So if I find the rock granite, right, and I find the rock gabbro, they're going to have different minerals in them. I can find the exact minerals in those rocks by following the edges straight down, and I can see the names of the exact minerals that will be in those rocks directly below in the mineral composition chart. So in a granite, I would expect to find potassium feldspar, quartz, plagioclase feldspar, biotite, and amphibole, whereas in a gabbro, I would expect to find different minerals, mostly plagioclase feldspar, pyroxene, olivine, and amphibole, with a little bit of biotite. So we can figure out where these rocks would form based on how they look, right? So we look at their physical properties, and then we can infer what type of location. So we might have a mid-ocean ridge or a hotspot volcano. Hotspot volcanoes form in the ocean. But the rocks come all the way to the surface, so they would be extrusive, but mafic. A continent volcano, since it forms on a continent, wouldn't be mafic, it would be felsic, but it's still a volcano, so it's extrusive. So you can interpret the location based on the physical characteristics of the rock. And that is a quick overview of igneous rocks.